Okay, hello everyone. We should be live now, although I'm seeing an odd preview. Oh, I hope this doesn't mess up. My streaming software says it's displaying my tablet, and okay, looks good now. I'm trying to be able to switch between my slides on the tablet and my Visual Studio, and we'll see if this goes smoothly. So I just posted on Piazza about the final exam, and so you can read that and ask questions in office hours or on Piazza if you need to. We've got the Project 4 is available. Tomorrow, probably tomorrow morning, I'll make a video for Project 4, and I'll get the autograder turned on so that you can start making submissions. First biggest question, I'm sure, is what order should I do these three parts in? A, B, C. Just do them in the order they say. So A, you already have enough for. Part C, we're going to talk about today. And then part B, you're going to be doing some Google searching. But part C that we talk about today will help you understand what's going to happen in part B. So I haven't seen anything in the live chat yet. If someone could let me know that we're good and you can hear me and everything there. I know you're behind me by like 30 seconds. Okay, great, thanks. All right, so we're going to move on here. So today we're going to talk about a little bit of review, not too much, but we're going to keep mentioning the constraint satisfaction and optimization problems. And we're going to talk about backtracking, its general form, and we did the graph colorability yesterday. Today we're going to talk about the n-queens problem. And I'm going to show you an example of it written in Visual Studio. We're going to run it and see how it does on saving us time. And we're going to talk about branch and bound and how that is similar to backtracking except for optimization problems and how it's different, and specifically with the traveling salesperson problem, how we're going to do our branching and bounding. So we talked about this yesterday with what is a constraint satisfaction, what is an optimization problem, and we can, in a constraint satisfaction problem, we can stop when a satisfying solution is found if we only wanted one solution. Now, if we wanted all possible solutions, we would have to keep going. But if we're happy with one solution, we could stop her as soon as we find one. Or if we want more, we can keep going. When we have an optimization problem, though, there's two things that are going to be different. One is that we have to see how we meet that measurement that we're trying to optimize, and we have to understand that if we do stop early here, we might have a valid but not optimal solution because we don't know it's the best there is until we've tried every possibility. Now, we can rely on these two different algorithm families of backtracking and branch and bound for these two different types of problems if we can't find something better. So, for example, with MST, we don't have to do branch and bound to do MST. Even though it's an optimization problem, we have at least two greedy algorithms, two that we've gone over, that work just fine and always provide an optimal answer. In TSP, if we want an optimal answer, then we've got to do either a branch and bound or something else. And the greedy is not sufficient for TSP. So our general form of backtracking is at every point we must check to see if we have a valid solution, if it is still promising. So it is promising when we haven't violated any constraints. And we can check if it's still valid, have we reached the level of a solution? And if we, okay, Marcus says I should increase the volume from OBS, and I'm not sure how to do that. I've got my mic like turned up all the way, and so I'm not sure. I will look into that for next time. Okay, so anyway, so we if we're still promising, we check to see if we are at the level of a solution, like if we've colored all the nodes in our graph. If so, we can write out the solution, and we could stop somehow. Really, we don't want to exit. We would better yet throw an exception to cause someone at a higher layer to stop us. And then if we don't have a solution so far, then we have to proceed to make another change, and then we'll make a recursive call. So the solution, is it a solution, is usually a really simple test. Have we colored all of the nodes? Have we placed all of the queens? Usually a solution is just an if some number is equal to some size. Promising is going to have to change for every application that we want to solve. We're going to need a different promising function that is specific to that domain of problem. And the check node is just the generic name of this function. We could rename the function and call it something else, like put queen. We're going to look at it in a little bit. So the example we're going to look at is n queens, and a little review if you're not familiar with or don't know chess or haven't done it in a while. When we have a queen can move in the 4 cardinal directions, up, down, left, right, and it can move along the 4 diagonals. What we want to know is, oops, now I've got written over the top of that, for n equals 1, what we're asking is, can I place one queen on a 1-by-1 board so that it doesn't threaten to take another queen? Well, that one's pretty easy. If there's only one queen, there's no other queens for it to threaten or to be threatened by. Okay, what about n equals 2? Well, we can run through that one fairly quickly. Here's my 2-by-2 board. If I put a queen there, then I can't put one here or here or here. And if I start my queen in any one of the other 3 positions, I would run into the same situation. I'd just rotate this map 90 degrees each time, and there's all 4 possibilities. N equals 2 does not work. N equals 3 gets a little bit more work. So if I have a 3-by-3 chessboard, if I put a queen there, then I can't put anything else in row 1. I can't put one there or there in row 2. If I put one here in row 2, then I can't put one here because of that queen. I can't put one here because of that one. And I can't put one there because of both of them. So nothing works if I put it in the upper left corner. If I start it in the middle of the top row, then I can't put anything else in row 1 or row 2, so that's a fail. The upper right corner would be the same as the upper left corner, so n equals 3, no. What about n equals 4? That's going to get a bit harder. N equals 5, 6, 7, etc. It seems to be, as far as we can tell, n equals 1 has a solution, and everything from 4 up has a solution. 2 and 3 seem to be the odd chessboards that have no solution at all. So what we're going to look at is, first of all, how much work does this take? Well, if I check every possibility, and this is for n equals 8, if I calculate 64 choose 8, that gives me that ludicrous number there, 1.8 times 10 to the 14th power. So that's pretty terrible. If I restrict it with just a little bit of sensibility added, we notice that once we put one in the top row, we can never put another one in the top row. So what we could do is, oh, no, hold on just a second. My computer is telling me it needs to restart to install something. That's a cancel. Okay. If we ever put anything in the top row, we can't put anything else in the top row. And so we're going to apply that everywhere. Once I put a queen in row I won't put any more queens in row I. I'll move to row I plus 1. So with just that extra checking put in there, we get it down from 1.8 times 10 to the 14th power to a little over 16 million. Now, of those 16 million, there are 92 possibilities that give us solutions. Now, where did I get the 16 million? That's equal to 8 to the 8th power. So for n queens, we've got O of n to the nth power exponential. That's fairly terrible. So we want to reduce that search space. So for example, when we're doing our backtracking, we start in row 1 and we put 1 in the first column. Actually, let's go to zero-based. Let's call this row 0 because we're going to look at some real code in a few minutes. So I put 1 in row 0 and I'm never going to place another one in row 0. I go straight to row 1 for the next queen and I notice, oh, column 0, column 1, can't put it there. All right, let's try column 2. I put that one in and then I discover that now every position in row 2 is invalid. So we backtrack back to, sorry, I forgot that I had words here that go to one-based indexing. I should update these to be zero-based the whole way through. Sorry about that. So we go back to the previous row. Let's just say previous row. We go back to the previous row and try that position. So after we do that, then we discover there's 3 positions in that row that are invalid. Now really we would probably discover them from left to right. So we discover the first position is invalid. The next one, I could put 1 there, but then I run into no choices in the last row. And then I would discover the other positions in this row. I'd discover this one is a no, that one is a possibility, but then nothing else works. Then I'd discover that's a no, that's a no. So those are all invalid, so I have to go back to the very first row I tried and move this first queen over to, move this first queen over to this position and start all over. Now, when we print out this, the results of this search, we could require 1 solution, we could require 2 or 3, or we could print all of them. Several is usually not what we want. It's usually going to be 1 and stop, or give me everything that you find. So what we're going to look at here is how we're going to make this work. Our general solution is pretty simple. Have we placed n queens already? If we have, then we're done. Our check node is this specific to n queens, and we're only going to make more calls if it's still promising and we're not a solution. We'll make more recursive calls. And we'll try a new row, and we'll try every position within that row. The promising function is where we have to do a lot of work, is if I had some data structures, to remember, is a particular column available or not? So the row is easy. I always move to the next row. But then when I want to try the different columns within this row, I want to know, hey, is column 0 still available? It's available if there's no queens in column 0. Left diagonal and right diagonal is basically is upper left to lower right or upper right to lower left. Is there anyone in this diagonal? So we're going to check for a given row and column, is there anyone there or not? And for a given diagonal, is there anyone there or not? So I will determine if we can put something in this row at a given column. Now, what we're going to look at is I'm going to add a blank slide in here and we'll go through this. It says if we did 4 queens, we would have an entire tree with 2 to the 56th leave. That's our 4 to the 4th. Okay, so let me add a blank slide in here. And then I'm probably going to have to, yep, okay, I got to do the rotation nonsense and restart it so that we get a better view of the slide. Okay, so let's start with our zero-based numbering. I'm going to say, hey, I would like to, actually, instead of rows, let's just give them letters. So let's start out with, we'll just draw a chessboard, A, B, C, D. I'm going to give every position on the chessboard a letter. E, F, G, H, I, J, K, L, M, N, O, P. All right, so we're going to start out. We're going to say, hey, let's place one in row 0. In row 0, let's try putting one at A. All right, so I put one at A, and then I immediately move down to row 1. So I go down to row 1 and I try AE. Is AE still promising? No, because that one gets taken. Okay, we can't do AE. How about AF? No, that's on a diagonal. How about AG? All right, AG is valid so far, so we can go down to row 2. So we can try AGI. Right, AGI, well, that I is straight below the A, so that's not valid. All right, how about AGJ? Well, that J is on a diagonal with a G, so that's no good. AGK, no. AGL, no, that's on a diagonal with the G. Okay, so none of those work. So we backtrack to, we've tried everything in row 2. We go back to row 1 and we finish going through a loop. We make a new choice in row 1. So new choice in row 1, we go to AH. All right, so once we're in AH, we try AHI. AHI, no, that I is still below the A. AHJ. Let's see, what about AHJ? Looks okay so far. We haven't violated any constraints, so we can move on to row 3. Let's put a queen down in row 3. AHJM. Nope, that M is straight below the A. AHJN. No, the N is on a diagonal with the H, and it's right below the J. AHJO. No, because the O is on a diagonal with the J. AHJP. No, because the P is straight below the H. So that's a no. All right, we've exhausted everything in row 3. We go back to row 2. Whoops, I can't see the chat anymore. Gotta fix that. Okay. So we go back to row 2 and we make a new choice in row 2. AHK. All right, AHK, no, the K is on a diagonal with the H and it's on diagonal with A. Either one would disqualify it. AHL, L, no, the L is right below the H. And so that's invalid. So we have to backtrack to row 1. We've run out of choices in row 1. We go back to row 0. And let's change colors here. So we go back to row 0 and we put one in position B. All right, after we choose B, we try BE, no, BF, no, BG, no, because those are all taken by B. How about BH? We're getting a little crowded here. Good thing I changed colors. So BH is still valid. How about BHI? Right, BHI still looks okay. It's not on a diagonal or anywhere or in a straight line. All right, so BHI is still valid. How about BHI? And then we can go down to row 3. BHIM, no, because that's right below the I. BHIN, no, that one's on a diagonal with I. and it's straight below B, BHIO. BHIO looks like we've got a solution. So we found our first solution. Let's look at what we explored so far. We found 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 dead ends, and 1 solution so far. So that's 19 branches we explored until we had to stop, and 19 right there. We did it right. We didn't make a mistake on it. So we explored 19 branches before we found our first solution, and we got to our definition of promising, etc. We've already seen that. So, oh shoot, I forgot I had a blank slide for this, but the title would have been in the way anyway. Okay, anyway. So the pruning allows us to avoid these branches, and it allows us to cut out a decent section of the search tree. If I can make a move in row 0 and then eliminate things in row 1, then I'd never go to row 2, row 3, row 4 if my move in row 1 is invalid. That cuts away a lot of our search space. I never explore AE anything. I never explore AF anything. So the promising is where a lot of the work goes, and a little bit in the recursive function. So there's some work to do when we write a new one of these. There's work to do in the recursive function, and there's work to do in promising. So we know already that every row will have exactly 1 queen. We know every column will have exactly 1 queen. The first one is easy. Every row is easy. We just go to a new row. Every column will have exactly 1 queen. Well, we can't always place them from left to right, as we just saw with our solution. So we're going to have to keep track of, is this column in use or not? Every diagonal will have at most 1 queen. And so writing this, I found it wasn't useful to represent this as a 2D vector because the 2D vector got complicated to reason about. It involved a lot more looping than I wanted. So what I did was a bunch of 1D vectors of the row position, column, and diagonal availabilities, and we'll look at examples with a 4x4. So here's the real data structure with real zero-based indexing. And so the position in the row, because we know there's only 1 queen in any given row, we just need an unsigned integer to tell us which position is a queen in this row. And if there's no queen in this row yet, we won't look at the position. So if we know we haven't placed one in row 3, we won't even look at position in row sub 3. For the columns, is a column available? I'm going to use true or false. So I'm going to use true or false, and I'm actually going to create a named constant for available, and that way I don't have to remember if column being true means there's someone there, or column being false means there's someone there. I'm going to just check if column sub I is available. If it's equal to available, that means I can put 1 there. So that'll eliminate a little bit of confusion. So this is an example where we would say columns 0 and 2 are available, columns 1 and 3 are not available. Then with the diagonals, what we're going to do is we're going to start indexing at the upper left diagonal. So this is diagonal 0, 1, 2, 3, 4, 5, 6. So there's how we number the diagonals. We start with the upper left diagonal. And for example, here with those queens placed, we see diagonal 1 and 4 are marked as not being available, and all the other diagonals are available. And then for the right diagonals, we start our indexing at the upper right. So we would say this is diagonal 0, 1, 2, 3, 4, 5, 6. And so we can see that diagonals 1 and 2 are not available, all the others are available. And here's how we index. I forgot to do that on the previous one. So here's our formula for how we index the upper left to lower right diagonal. We use row plus column, and when we do the upper right to lower left diagonals, we do that formula there. You don't have to know the formulas. We're not going to put these formulas on the exam. I just hate giving half answers. So this is how we turn a row and column into a diagonal number. And that's going to be important in the implementation, but not critical to understanding what we accomplished. Okay, so here's the promising function. So the promising function says, hey, I'm going to give you a row and column. Wait a minute, where's everything else? We have a class. So in the nQueens class, things like column and left and right diagonal are all member variables. So we ask the promising member function, is this row column promising or not? And so we check if that if that column is available, if the left diagonal and the right diagonal are all available. If all those things are available, then it's promising to put one there. And we don't check, notice we don't check the row in here because we're always going to ensure that we put one in a new row. Then here is, and there's a lot of code here, here's the actual put queen function. Now remember I said we could change check node to a more specific name. So this is check node for the nQueens problem. So the very first thing here, I reordered the code a little bit to make it more convenient for this particular problem and the way I formulated it. So we first check, basically, do we have a solution? We're not going to call this function with an invalid situation. So we're only going to make a call to this put queen if there's no violations and constraints. So if we have reached the level of a solution, if the row number we are on is equal to n, we could print solution found. Actually, the real version is going to print out the chessboard, but I wanted to fit this all on one slide. So if the row number we're trying to place a queen in is equal to the number of rows total, we'll say that the solution is found and return. We're done, base case. Otherwise, here's our recursive function. We're going to run through every column in this new row. So we're going to run through every column and we're going to check, is it promising? If I were to put a queen here, would it still be promising, is what we're doing in this function. So we ask promising, would it be valid to put a queen here? And notice there's no else clause. If promising says false, we go back through the for loop and we try a different column. If none of the columns turn out to be valid, if all the columns in this row turn out to not be promising, the recursive call would end and we'd go back to someone else's loop where they were making recursive calls. So if this row and column is promising, this is all the things we do to actually make that move for this row comma column happen and record it in the member variables so that we know what's happened. Then we make our recursive call. Then after the recursive call is over, we have to undo the move. See, this is the thing that's a detail that's hidden in pseudocode. In pseudocode, we just say, make a move, make the recursive call, and undo the move. We might not even do that. We might just, in our pseudocode, we just said, make a recursive call. When we need a real implementation, though, we've got to worry about these things. So notice that everything that used to be marked as not logical, not available, everything that used to be marked as not available is now marked as it is available. There's one thing we didn't undo, and that was the position in row never got changed. Remember, I said we're never going to look at a position in row if it's not valid. So we put something in this new row, then when we go back through, we don't actually change what's in there, we just make sure we don't look at it. But the Booleans, the not available changing back to available, is critical to undoing that move. Think of it also in 280 terms in terms of preconditions and postconditions. Because promising said this row column was valid to make a move, before we did anything, it was available. We marked it as not available. Then after the recursive call is done, we have to put them back to where they were available, so that we can go back through the loop and try other positions within this row. If we leave this one as marked as, hey, this one's already taken and the other diagonals are taken, we'll never be able to put many queens anywhere, because we'd leave everything would get marked as not available and it would never change back to available. So that's how the code works. Okay, that's traveling salesperson. So what we're going to do here is we're going to switch over to Visual Studio, hopefully. Okay, now my broadcasting software says that we're on Visual Studio, and when I go to Visual Studio, I'm not going to be able to see the chat for a few minutes. I've got limited screen space here. So before I change over fully to Visual Studio, just want to let me know if you can see Visual Studio now. Okay, great. Thanks for the update. All right, so we're going to switch over to Visual Studio here. Okay, so and this code is in Canvas. It's in the Files sample code folder. It's all in there, so you can look at it at your leisure later. Now, before we look at the code, let's run this. And by hand, I've got to switch over to my output window. Okay, so you should be able to see the output. So we're going to run 4 queens. So that's the one we already did by hand. Display the results. Yes, we do want to see the results. So it runs through it, and I'm going to make this a little bit bigger. Hopefully the video will adjust properly. So there's the whole output of the program. We placed 4 queens. We displayed the 2 boards. So every time it finds a solution, it says solution found, and it displays the board. Then at the end, there's extra code in the real solution that's not in the slides that does the actual displaying of the board and a little bit of statistics. So there were 2 solutions. We explored 60 branches out of 256. That's our 4 to the 4th. And a savings of 76%. That's how much of that possible search tree we pruned away. All right, now let's run it again, and you're going to go black for just a second. Okay, so we're going to run it again, and let's do it for more queens. Let's try like 10, and we're going to say no here. We do not want to see the results of that. Okay, 724 solutions, 348,000 branches out of 1 times 10 to the 10th, that's rounded off, and a savings of 99.9965%. Pretty good. All right, let's go bigger. We can go bigger. I made sure I did this as a release build, not a debug build. Let's try 12 queens. No, we definitely do not want to wait for the results of 12 queens, because there were 14,200 solutions, lots of branches explored out of an even more crazy large number, a savings of 99.9999%. That's how much of the search tree we pruned away while we were doing this search. Okay, so let's close this, and we're going to go back to Visual Studio and look a little bit more at the code here, how it's organized. So I've got my n queens header file, has what goes into the class. We've got the size, which is in the slides it's referred to as n. Here I called it size since I had a little more space. We've got some longs for solutions and tried, that's just statistic stuff. And hey, here's our vector of position in row, our vector for the column, left diagonal, right diagonal. Here's our named constant for available. Here's our private functions. So I've got a private, put queens as a private function. See, the public functions are make me a board of size n, solve it, and give me some statistics data. So the private functions are that put queen, our recursive function, gets called by solve, and then put queen calls itself, put queen calls promising, and put queen calls display board. If we go over to nqueens.cpp, we've got, here's the remainder of our named constant, available is true, and then we've got the constructor, just remembers the size, sets the solutions and tried to 0, sets our vectors, so these are our vector constructors doing their sizing and their initial values. Everything's marked as available to begin with. Solve function, the display is whether or not we want to see the things displayed. Calls put queen of 0 and whatever display is. Here's promising directly from the slides. And here's our recursive function. The only thing that's different about it is a little bit of statistic stuff and the call to display board. And let's see, a little bit more of statistics in the recursive function. Rest of it's the same. And then the display board function is just our code there. You can look at that later. And then one thing I forgot to mention, I sort of glossed over it, is the recursive call, which is the same as in the slides. When we make a recursive call, we always call it with row plus 1. So whatever row I'm in, I say, okay, I have made a move in this row. Let's make a recursive call to the next row. I know I've got to move on. So that's how we prevent it from ever putting two queens in the same row, is by making a recursive call with row plus 1. Now, if anyone has any questions, I'm going to leave Visual Studio up for a minute. I'm going to go back to the chat and see if there's any questions I need to answer about the code. And like I said, that's all on Canvas files sample code. Just if you try to do anything bigger than like size 8, make sure you've got an optimized build, not a debug build inside of Visual Studio or Xcode. Yep, okay, thanks for watching the chat. All right, so let's go back to the slides. Change over here. Okay. So now we're going to start talking about branch and bound and TSP. So we've got an XKCD comic here. So the brute force solution to traveling salesperson is O of n factorial. And that's actually where we're going to be, except we're going to prune. So notice how good of a job we did pruning the n queens problem. We pruned away 99.9999% of the search tree just with 12 queens. So we'd like to hopefully get a lot of pruning like that. Even though we're not quite going to do brute force. We're going to do branch and bound. But it starts out as n factorial, and we're going to cut sections away. Is it still n factorial? Really hard question to answer. Now, if we were doing things in a different order and we had another couple weeks just for this topic, we could look at how the dynamic programming algorithms solve traveling salesperson. So dynamic programming solutions solve this in O of n squared times 2 to the nth. And normally we'd say, whoa, 2 to the nth is your improvement, but yeah, 2 to the nth is an improvement over n factorial. The neat thing is the comic here actually shows how you can do it with dynamic programming. It's called a cutting plane technique. So the dynamic programming does a cutting plane. It does different combinations of where the cut goes, and then it uses dynamic programming to save intermediate results and build those back up into an optimal solution. Now, granted, traveling salesperson, there are not a lot of people anymore who are traveling salespeople who come to your door and sell you a vacuum. That's outdated, and people would say, oh, well, hey, we just sell it on eBay. It's O of 1. But this problem comes up over and over and over again. If we're routing traces on a circuit board or on a processor, similar problem to traveling salesperson. Simple one that still happens every day in physical world is, hey, we've got a delivery truck. We just put 175 packages on the delivery truck, and we want to have the minimal amount of time and or gas spent delivering all those packages and returning back to the warehouse to pick up another set of packages. So this problem comes up all the time. Even though traveling salesperson is a little bit outdated, the name of the problem remains. Well, true, nobody's traveling but our UPS drivers are still out there delivering things. Like hopefully tomorrow, the UPS driver is delivering Professor Darden's new Mac with more power so that he can do live broadcasts on his Mac. So before we get into what branch and bound is and how it relates to this, we need a little bit more about traveling salesperson. So first definition, Hamiltonian cycle. If I gave you a graph with vertices and edges, I want you to find a cycle that traverses every node exactly once. You're never allowed to visit any node except for the first one will be the same as the last one. So other than that, we've got to have a cycle that hits every node once and returns to the starting point. So that would be a Hamiltonian cycle. That's a constraint satisfaction problem. Can you do it? The traveling salesperson problem is, if there is a Hamiltonian cycle, I want you to find me the one with the minimum weight, with the least weight. That becomes an optimization problem. So we're going to solve the harder one. We're going to solve the optimization problem. So one of the things we're going to do is we're going to extend the idea of backtracking. So one is that, well, first of all, if we violate constraints, we backtrack. We're not going to continue to try to optimize if the solution will never be valid. Next thing that we could do is I could say, hey, if I've got a partial solution, like I'm supposed to make 50 deliveries, and my proposed route right now, the one I'm thinking of, I've got a proposed route of the first 30 packages, and the route for those first 30 is longer than the best 50 complete cycle I know so far. This is a bad partial solution. Let's get rid of this one. Now that will help. That will prune some, but we need to do more pruning than that. Just knowing that a partial solution is worse than the best so far is not enough. We need to do more pruning to get rid of bad looking solutions. Because the better the job we do pruning those solutions which don't look good, the earlier we do that, the less time we spend on it, and the faster we solve the problem. And so the more accurately we can compute a partial cost, and we'll talk about what that means in a second, the more accurately we can compute a partial cost, the earlier we can prune. And so we might want to spend a little bit of time on this partial cost estimate to get a better bound. So let's look at an example. So here's, we've got 6 vertices, and you'll often find that when we present problems like this, the numbers don't make sense in a Euclidean world. You could say, oh, well, this is travel time. And those ones that look short but have a long length, those are just more crowded roads, and it takes longer to drive on them. So ignore the fact that this does not fit a Euclidean graph, but we wanted to make it fit. So here's a bunch of nodes and edges and weights associated with them. And there's a possible solution. In fact, that is the optimal solution. So how did we get there? Well, we start doing, oh wait, sorry, we got a little bit of history first. Before we get that one done, here's a little bit of history. So now, basically 66 years ago, 66 years ago, TSP was solved for n equals 49, and you can see kind of the light blue, there's an outline of the US. There's Texas, Florida, there's an outline of the US, and someone solved it in 1954 for n equals 49. 49 big cities TSP tour. That was state of the art back then. 16 years ago, someone solved for Sweden 24,978 places. Yes, exactly, Alex. So 16 years ago, someone solved it for Sweden. Basically, every place that had a name, they put it in the TSP tour. And there's a link there you can look at how they solved it and how long it took. Solving that problem with 25,000 vertices took basically years of compute time, using lots of computers at once, years of compute time just to improve a solution. When we run TSP finding optimal solutions on the autograder today, we're never going to give you more than 40 because it would take too long. We want it to finish in 35 seconds or really significantly less. We want to finish in like under 10 seconds. So we can't give you too big of problems. Even though bigger problems are solvable, it needs an army of computers to solve it in a couple of years. And these are actually small problems compared to, say, routing among transistors on a CPU that has a few billion transistors. So here's our TSP search with backtracking. This is no branch and bound. This is no optimizing yet. There's no pruning due to optimality here. This one just has branches that we eliminate because there's a dead end. So notice the first one here that we have marked is A, B, C, F, E, D. So that would be in the I'm going to change colors here. In the diagram in the upper right, A, B, C, F, E, D, and now I can't get back to A. Now, in your part C, when you're solving this, you don't actually have to worry about this. In your part C, the graph is completely connected, so you'll never run into a dead end where you cannot finish the tour. So let's look at what we want to do to branch and bound. So the first thing we're going to do is we're going to start with a bound of infinity. The Infiniti Bound, think of this as our best so far. My best cycle length so far is infinity. Let's improve on that. What we can do then is the very first complete solution we find, no matter how good or bad it looks, it's still going to be better than infinity. And then that becomes our new best so far. And then as we do subsequent searches, we want to know, does my complete solution, is it better than the best so far? It becomes the new best so far. And when the search is done, when we've searched everywhere, the best so far we've ever seen is the best there can possibly be. Now what we want to do is, we can ignore the dead ends. What we also want to do is we want to get an estimate of what is my remaining cost. So for instance, we find, if we started out with infinity, we would find the 27 is our best so far. 27 is now our best so far. And then as we backtrack and try other branches, every time we have a real cost, we want to get an estimate of what it would take to finish this cycle. And if you can give me that estimate faster than it would take me to actually finish it, I might save some time. So for example here, if we look at the path where this box is 23 plus 8, so I go A to B, B to C, C to D, and D to F. So A, B, B, C, C, D, D, F, that's where the 23 comes from. That's the real cost so far for AB, BC, CD, DF, sums up to 23. Where did the 8 come from? Some magic function that we haven't written yet is our estimator. What's our estimate of the remaining cost? So I ask the estimator and it says 8. I say, well, 23 for my real cost plus 8 for my estimated cost, that would be a total of 31. That's not better than 27. Really, if it's greater than or equal to, it's not promising. If it's not less than, it's not promising. So we would eliminate things that are invalid. Hey, in our project 4, part C, we don't need to worry about that. We're going to eliminate any one that doesn't look like it's going to be better. So we've got to have this function that gives us an estimate of the remaining cost. So we need to, so we don't usually have these min cost values. We need a function to estimate those. So when we're doing this, we've got some of them that are connected so far and some are not. What I'm going to do is I'm going to say, hey, for the ones that I don't really know what the path is, I want an estimate on the unvisited nodes, unvisited vertices, and I want that estimate to be the lowest cost possible. Now let's go back to why that has to be the lowest cost possible. If I ask the estimator, like up here, at some point I was here. AE, let's see, so AE and ED. So with AE plus ED, I have a little bit trouble seeing it. We got 3 plus 1 is 4. So right here I've got 4 plus question mark. If the estimator were to say to me $1 million, I would say, ooh, 4 plus $1 million, that's not better than 27. Let's prune this branch away. So the estimator can't be too high. If the estimate is too high, we might prune away the optimal branch, which this one is. We're in the optimal branch right now. So if the estimate is too high, we might prune away the optimal branch. What if it's too low? What if the estimator says 0? If the estimator says 0, then everything looks good and we don't prune anything. So we're actually kind of playing the prices right here. We want the actual retail cost of finishing this tour without going over. If we go over the actual cost of finishing it, we might prune when we shouldn't. If we're under a little bit, that's fine. If we're under by too much, we won't prune enough and we'll be too slow. So that's why we'd like to be as good of an estimate as we can, but we've got to make sure that we don't overestimate. Okay, so we've got a real path so far. We've got to find some way to connect the unvisited vertices all to each other, and we need to connect the visited to the unvisited. Now it's possible this might not make something that looks like a cycle. I don't care. I don't care what it looks like. I just care about the numbers. Do the numbers make it look like it might possibly be better than the best so far? So let's look at an example here. Oh, wait, before we get to let's go to the example, then we'll come back. All right, so here is what we have so far. Current path ABC is where I am. I'm at C, and I'm trying to pick somewhere else to go. But I want to know, does this look good so far or not? So I add up the real cost, A to B, B to C, and then I need to connect D, E, F, and G together. Just D, E, F, G, let's connect them together, and I want to get the lowest, I want the best way to connect them together. Best meaning it cannot possibly be an overestimate of the best way to connect them in the cycle. So if I were to connect them like that, what does that look like to you? So just the unvisited connected together here looks like something we're familiar with. Looks like an MST. So I could make an MST of those. I know that can't be an overestimate because there's no better way to do it. There are longer ways, but there's no shorter ways. So this can't be an overestimate. But I want my estimate to be as close as possible to the real cost of finishing this tour, and I don't have enough edges yet. I'm still too far under. Well, if I started out ABC, I know it's got to go ABC, C has got to go down here, and then this region has to come back to A. So I need 2 more edges. Right now, I've got 2 black edges are the real edges. 1, 2, 3 gray edges are my MST. A real cycle of 7 vertices would have 7 edges. It's like someone said, point that out earlier. So we know we need 2 more edges. So what we can do is find the closest vertex to the, let's call this the start of the path. Let's find the closest unvisited to the start and the closest unvisited to the last. They could be the same vertex, or maybe they're different vertices. I don't care. They've got to be an underestimate. If I find the closest one to A and the closest one to C, I know it's not an overestimate. Can you get more complicated? Sure. I could find the closest one unvisited to A or C. Find the absolute smallest from A or C to any unvisited, and then take the shortest one that doesn't go to the same vertex. It's harder to code, it takes a little longer to find, it produces a little bit better estimate. Is it enough? Is the extra work pay for itself in more pruning? Not sure. But we know this is an underestimate. If you try to find the shortest edge and the second shortest edge, the shortest edge that goes to the opposite vertex, you could end up with a mistake. It's more easy to get that wrong. This is sufficient. So we add up the black, our real path, the blue and the gray, our estimate. If that total is better than the best so far, we would say, yeah, this looks like a good beginning. We should keep going this way. And if that total comes out higher than our best so far, we would say, no, it's not. This one looks like, yeah, ABC could look like a valid solution. In fact, I would bet that with this graph, a valid solution is either going to start ABC or it's going to end CBA. Either way, doesn't matter. Your program does not have to worry about finding it in one direction versus the other direction around. Don't worry about that. Really, really hard to eliminate that. One thing we are going to do is we require you to start at vertex 0. Because it doesn't matter. If I had, let's say, 3 vertices, I've got vertex 0, 1, and 2. Does it matter if I go 0, 1, 2, and back to 0, or whether I start at 1, 2, 0, and back to 1? No, doesn't matter. Same cost. It's easy to not repeat every possible starting point. So going around the circle one direction versus the other, don't worry about. You do want to make sure you only start at vertex 0, and we'll talk in a few minutes about how to do that. So here's how we can make our estimate. Let's go back a few slides to the estimator complexity. So we said the estimator must be less than or equal to reality. With a few different vertices, maybe the MST plus the connecting edges would actually look like the optimal tour. I picked an example that doesn't. So the estimate must be less than or equal to reality, and it should be faster to calculate, would be good. If it's slower to calculate than finishing the tour, that would be bad. You know, if it takes k factorial, if k is the number of vertices we haven't visited yet, if the estimate takes more than k factorial, it's terrible. It's got to be better than k factorial, like k squared. So, for example, here, in k squared time, I can do an MST. In 2k time, I can find those connecting edges. I loop through it. I loop through all the unvisited. I find the shortest distance to the start of the path. I find the shortest distance to the last thing in the path, and I can do that in 2K time. So now I'm going to add an extra blank slide here, which is going to require rotations and shuffling to get it to appear in a little bit better light. Oh, wait, no, not too bad. It came through this time. Okay, so let's look at different values of, so this is the number of unvisited is equal to K. Now, so I've got my K, and I wanted to figure out the cost to finish the tour or the cycle. C-Y-C-L-E, I can spell. So if I wanted to finish the cycle, it would cost K factorial. If I want to do the estimate, it would cost K squared plus 2K. All right, so let's go big K first. If there's 10 vertices remaining, the cost to finish the unvisited vertices would be about 3.6 million, approximately 10 factorial. However, the time to do the estimate would be 120. So if I spend 120 operations doing the estimate, if promising still says true, I've added 120 work. But if promising says false, I've eliminated 3.6 million work. That's a big win. All right, let's try small k's. K is 1. So finishing the cycle is cost of 1. Getting the estimate is a cost of 1 plus 2 is 3. Okay, what about 2? 2 factorial is 2. 2 squared plus 2 times 2 is 8. It's costing, at the small end, it takes longer to do the estimate than just finishing the darn thing, okay? What about K equals 3? 6. And now we've got 9 plus 6 is 15. All right, how about 4? 24 and 24. You'd say, ooh, you broke even. You should do the estimate. Well, if I do the estimate and it still says that it's promising, I still have to pay the 24. So here I've either replaced 24 with 24 or I've replaced 24 with 48. Not a win. What about 5? 5 here would be 120, and this would be 35. That's maybe looking reasonable. I either decrease my work by like 85-ish, or I increase my work by 35. What about 6? 720 versus 48. That's probably a win. So the point here is that when the number of unvisited vertices gets small, you're better off just finishing the cycle and not even calling promising. Or better yet, we call promising. Promising says, you know what, there's so little work left remaining, I'm just going to say true. So what we can do is, in our promising function, just check the number of unvisited vertices. If the number of unvisited is small enough, what's small enough? It's not an exact value. You can play with it a little bit and check your speed. If it is small enough, promising can just say true, and then the recursive function will continue on that path trying it out, because it would be faster to finish it than to do the estimate. Okay, so here's our general form. We're going to check, is it promising? Is it a solution? If it's a solution, then we will update the current best if it's better. So if it's a solution, we'll update our best if this new solution is better than the best so far. If it's not a solution, if we've got more things to do, we make more recursive calls. So our solution is really simple. Have we visited all the vertices? That one's easy. Our update is we check, make sure the cost of the new cycle, the whole cycle, if that's better than the best so far, we update our best so far. And our best so far is really going to be two things. We've got to remember what is the cost of the cycle and what is the order that we visit the vertices in to print out the cycle. And check node is just whatever our recursive function is. Lower bound is going to be called by promising. So promising will do our check that we just talked about. If the unvisited is small, promising will just say true. But if the lower bound function returns the estimate plus the cost so far, if that lower bound cost is less than the best so far, promising says true, otherwise promising says false. So these are the things you have to write. What we're going to give you is, we're going to give you the, we'll get to the code in just a minute. So if you do a little bit more work on the bound, you might prune a little bit more. However, you don't want to make the calculations of the estimate too complicated. If you make the estimate too complicated and spend too much time on it, then even though you're pruning more, you may not make up for the cost of doing the estimate. So you want to make sure that your estimation cost is in the k-squared range, where k is the number of unvisited. And if you're doing MST plus the connecting edges, you'll be fine there. So what we're going to give you is gen_perms. And this is a slightly different version than the one we did earlier in the semester. This one's more efficient. You want to make sure to use this version. This version is the one that is posted in the CPP, the text file in the Canvas folder, genperms.txt. So let's look at what this says. Is you give me the path and the perm length. What perm length is how much of the path is fixed right now. So for example, if path was, let's say, 0, 1, 2, 3, 4, 5, 6, and perm length, let's say perm length was 2. What that tells me is that 0 and 1 are fixed, and these are the ones that can still be permuted. These are the ones that can be changed. Notice that in every recursive call, perm length goes up by 1. We have fixed a new vertex and made a recursive call. And the code here is not complete. It's enough to give you a starting point. Notice here, there's no, I passed in path. Where are the vertices? Where are their x and y's? How do I calculate distances? Don't add more parameters to this function. What you should do is make this a member function of a class. Get rid of the template and decide what's in your path vector. Make it a member function and then get rid of this as a parameter. And pass the perm length is the only parameter. Everything else will be member variables. If you don't do that, if you just add like 6 more parameters to this, this call at line 11 is not tail recursive. How many times is line 11 going to happen? Possibly n factorial. So if you push 7 or 8 things n factorial times, and I push 1 thing n factorial times, guess who's going to run faster? So we want to get rid of the path, make it a member variable, and just pass perm length. You could eliminate perm length by making it a member variable, but it gets a little bit more changes to the code. If you just get rid of path and make everything else but perm length a member variable, you'll be fine there. So how does it do it? You don't have to understand like lines 10 and 12 how they make every permutation happen, but what is important to understand is what they do. So it says swap something with path sub perm length, and then make a recursive call and then put it back where you got it. So we have a precondition. Right now, this is the path. Then I swap something, I make a recursive call. After the recursive call is over, I put the path back like I found it. So, for instance, when we start out I is equal to perm length, when I is equal to 2, we swap 2 with 2, which doesn't do much. we make a recursive call. But when we make the recursive call, perm length is 3 in the recursive call. That's saying 0, 1, 2 is fixed, permute the other ones. Then when that's done, we put 2 back where we found it, swaps with itself, but then I becomes greater. I moves up to 3, and we swap path sub perm length, which is 2, with path sub I, which is 3. So now the path becomes 0, 1, 3, 2, 4, 5, 6, and we make a recursive call saying that is fixed, permute the others. Then when we get back, we put the 3 back where we found it, and then we increment I, and we swap the 2 and the 4. And we say, okay, now 0, 1, 4 is fixed, make a recursive call and permute the others. Then when we get back, we swap them back, and we say swap 2 and 5. Now 0, 1, 5 is fixed, make a recursive call where 0, 1, 5 is fixed, and the others are permutable. That's why when we get to line 3, if perm length is equal to path.size, we're at a base case. We do something. What do we do here? Well, basically we call the update. The do something is call the update. If we've reached a base case, we call update. We check what's the total cost of this cycle. Is it better than the best so far? If it is, update the best distance so far and the best path so far. What is best distance going to be? Oh, double. What is the best path? It's the same thing path is. In update, if it's better, we just say best path equals path. Let the vector object figure out the best way to assign one contents of one vector to another. When we are all done with this, it will undo everything it's done to path. When this recursive function is done and we're back to whoever called it, path will be back to the way it started, but best path will contain the best one you ever saw. So when you're all done, you would print out the double best distance and everything in best path. Where'd best path come from? Oh wait, it's another member variable. Best distance, another member variable. Now when you're doing this, you'll find 2 things that are important for optimization. One I already mentioned about the recursive calls. Let's cut the parameters down to just perm length. The other is, as promising says true. Let's say I had 20 vertices. I say, ooh, let's add up the cost of the current path. Well, I don't have any vertices so far, so the length of the current path is 0, and then let's do the estimate. Oh, that's promising. Now let's add up the length of the current path is this one edge. Oh, it's still promising. I do the estimate. Oh, it's still promising. Okay, let's add up these 2 edges and add up the estimate. Then I say, oh, that's promising. Let's add up these first 3 edges. It's still promising. Let's add up these first 4 edges. Oh, it's still promising. Let's add up these first 5 edges. You're doing too much work. What would be better is if we kept another variable, a running total. What is the length of the current path so far? And what we can do is, right before this recursive call, I could say like my current length plus equals the cost of this new edge. Then, after the recursive call is over, I minus equals the same cost. That way I've got a running total. Instead of adding up the first 2 edges, the first 3 edges, the first 12 edges, the first 13 edges, instead of doing that over and over, I add 1 to the current cost, and after the recursive call, I remove 1 edge from the current cost. That's going to produce one other thing you have to do though. When we get to here, in line 4, before we get the cost of the cycle, we're actually going to have something like this. And we're going to be missing that closing edge. We'll have to close the edge from the last thing in the path to the first thing in the path before we know what the actual current cost is. When this thing is all done, like I said, path will go back to where it started, and current length should go back to 0 or really close to it. If you're done and your current length is like 1 times 10 to the negative 15th power, no problem. It's just a little bit of round off error accrued over lots and lots of calculations. But if you're done and your current length is like 150 million, something went wrong. You plus equaled one length and you never minus equaled the right thing. So if when you're done, just check your member variable. If current length is 0 or close to it, that's an okay safety check that you didn't have your current length growing indefinitely. So then every time we want to call our promising, back here, when we want to call promising, we already know the black length. That's our current length. We have to calculate the blue and the gray. That changes all the time. Also, when we get to the update and we want to do update, we can say, hey, oh, wait a minute, I've got this one portion missing. I add this portion to the current length. If it's better than the best so far, I update the best so far, and I take this thing away. Whatever you add to current length, you got to take away from the current length. Otherwise, it would grow without bound. All right, let's see. Let's go back to our code here. Okay, I think that's most of the things important about the code here. So we've given you the starting point. Really, you got to add this to a class, add some more member variables, and put all these parts together. When we have to call the promising, that's going to be our MST, but it's going to be a little bit different from part A MST because two things. One, this MST doesn't care about medical versus normal. We always want straight Euclidean distance. If we worry about going through the border stations, then we might get an overestimate. If we get an overestimate, we overprune. If we overprune, we don't find the optimal solution. Other thing is we have different vertices every time. Like at one point, and I've erased my notes here, at one point I had to do the MST of like vertices 3, 4, 5, 17, and 23. And then at some other point I had to do the MST of 6, 8, 12, 14, 23, and 31. So what you have to call the MST on changes all the time. So you've got to make sure that your Part A code, that it has to allow for there to be a different number of vertices that get computed, that like if you maintain your prims table, that you don't leave small values and true in there. You got to set them back to false infinity. You've got to do only the unvisited vertices. Like simple mistakes would be things like, oh, I kept my prims table, but I forgot to set everything back to false infinity. Or I did the MST, but I always do the MST of 0, 1, 2, 3, 4. I don't do the MST of 3, 4, 5, 17, and 23. Easy mistake to make. You can have a perfectly working Part A and fumble the handoff when Part C calls Part A because you didn't set your table back to false infinity, you didn't do the MST of the right vertices, you always did like the first 5 or first 6 or first 7. So there's easy mistakes to make in there. If you find that you are always getting wrong answers, like it's always too long, then you're always over pruning. If you find that you always get right answers, but it's too slow, you're under pruning. If you get a combination of the two, like some test cases on the autograder, you're over time but right, and others you're under time but wrong, you're doing both. You're over pruning and you're under pruning. That's a good indication that you failed the handoff from Part C to Part A. What you can do there to do some debugging is put in an if statement. Like if, for example, if I were to tell you that the optimal path starts out, and you've got the sample output, you've got an optimal path that starts out 0, 5, 12, 17, 23, blah, 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 and your incorrect path, your best that you found is 0, 5, 12, 14, blah, blah, blah. At some point, you were here, and promising said false. Because you found the 14, it was okay, but you never found 17 in that position. At some point, 17 was there, and you said prune it. So what you can do is add in an if statement to say, hey, if path sub 0 is 0, oh wait, no, path sub 0 is always 0. If path sub 1 is 5, and path sub 2 is 12, and path sub 3 is 13, then print out some stuff. Print out things like what is your current cost of, actually what is the current path, what is in the unvisited, how many vertices are in the unvisited, what is your current cost, what is the MST cost. And in fact, what you could do is you could print out not just the MST cost that your estimator came up with, but print out the unvisited and print it in a format that's ready for part A. So I'd print out my MST cost, that's for my double checking, and then I would say, oh, there's like 7 vertices, this is the number of unvisited, and then I would print the XYs for those 7 vertices. If you use a file that doesn't have medical versus normal, if you have a original input file that's all up in the normal part of campus, I should be able to take this, copy, paste it, run it with part A, and get out an MST. So if my MST estimate says 400 and my part A says 300, aha, something failed, and now you can debug this one. When those 7 were in the unvisited, why did you get the wrong MST cost? So this will save you a lot of time in debugging. If you look at the sample files we gave you, there's a sample C is like a large number of vertices. I took sample C and I shifted everything upright until it was all in the normal part of campus, and all in the same region. And there's some notes. Read the README file. Will tell you what files have what in them, like sample D and sample E are all in the normal region, and so they should give you consistent answers. If you're running part A or part C, calling part A, and it tells you like what to do if you get this case or that case, what you should be looking at. A couple other things we need to cover. First is, how do we prevent ourselves from starting at vertex 1 or starting at vertex 2 or starting at vertex 3? Aha! When you call this the very first time, make sure that path has 0, comma, I don't care what else, make sure 0's in index 0, and the very first time you call this, call it with perm length 1. If you call this with perm length 1 the very first time, that's saying, hey, this much of the path is fixed, you're not allowed to change it. If you call it with perm length 0 for, let's say, 35 vertices, 35 factorial and 34 factorial, they're both terrible, but one of them takes 35 times longer than the other. So you just want to make sure you call this with perm length equal to 1 the very first time instead of 0. The other thing is we need to go back a bunch of slides to our starting point. Back to here. Start with an Infiniti Bound. Remember I said this is our best so far. If I start with a best so far before I ever call GenPerms, if my best so far is Infiniti, everything looks better. Terrible, terrible choices look better. So I could start out with a path that goes like this and crosses itself 100 times and then goes back to the beginning. Hey, that's better than Infiniti, that's great. Well, it's not great because Even after I get that one that's not Infiniti anymore, now I've got a solution that's 10,000 when it should be 1,000, and other things that I'd like to prune still look promising. So what I'd like is a bound. Let's not start with Infiniti. Let's start with a number. This number has to be greater than or equal to reality. It could be an overestimate like Infiniti is, but I'd like to be closer to reality than Infiniti. Where could we get this? Part B. So let's talk about part B for a minute. Part B is, hey, what if there were too many vertices for k factorial, or sorry, too many vertices for n factorial or v factorial to be reasonable, like 10,000? Well, I'd like to get what's called a heuristic. So part B involves heuristics. A heuristic is a way of solving a problem that isn't necessarily optimal, but gives you a reasonable answer in a lot quicker time. It'll be a valid answer. It will be a cycle that visits every node exactly once. It might be optimal. You can always get lucky with a heuristic, but usually it's going to be a bit longer, but it's going to run much faster. So part B, what you need to do is go Google, find some TSP, traveling salesperson heuristics, and try one or two of them out. You want to stick to things that are in the range. Whoops, I thought I had a slide for that. I don't. We want to stick to things that are in the range of v squared. We don't want to be longer than v squared. We want to stick to any heuristics that are v squared or better. We want it to be something that's possible to implement, and there's a number of good ones. If you look on the YouTube channel for 281, make sure to click on videos. Don't just go to the homepage. Click on videos and look for in there, I've got a MATLAB demo from a previous semester. And what I wrote in there was I wrote a simple heuristic in MATLAB and had it display, as it did all the updating, display what the cycle looks like as each new vertex gets added. And the heuristic I used was greedy nearest neighbor. So I've got a path like 0. I find the closest vertex to 0, that comes next. Then whatever vertex that is, I find the closest one to that I haven't yet visited, that's my next one. Then I find the closest unvisited to that one, closest unvisited to that one, and that's an easy heuristic to code, but it gives kind of solutions. It's v squared. It does give valid solutions, but they tend to be too long. You can implement greedy nearest neighbor and then add 2opt. 2opt is in the Project 4 tutorial slides, and greedy nearest neighbor plus 2opt will get you almost all the points for part B. Or you can find another heuristic. So lots of people will implement greedy nearest neighbor because it's easy. Then they'll run into problems with 2opt because it's a bit harder. And then they'll end up with a different heuristic anyway, because even if they get it working, it didn't quite get them all the points. However, greedy nearest neighbor is good enough for part B that you can continue on to part C and then come back to part B later. So like greedy nearest neighbor is good enough for part B to continue with part C. Greedy nearest neighbor plus 2opt is good enough to get you like 99.9% of the points, I think, on the whole project. And if you want the last 0.1, you got to come up with a new heuristic, implement a new one, and do some searching. So watch the video on the MATLAB demo to see why greedy nearest neighbor is not the best. All of the heuristics are greedy in some way. They just change how they're greedy. There's greedy nearest neighbor, there's a bunch of insertion heuristics. There's Christophides, which is more complicated and kind of hard to code. There's a bunch of different ones that you can look at and try out one or two of them. And we are happy to answer questions about them. And Profis hours especially, we can talk about different heuristics and how to do them correctly and how to optimize them. But we do want you to do some of this searching yourself and trying some of it yourself. If you find that a Part B heuristic implementation is going over like 40, 50 lines, you've got too long of a heuristic. You need a simpler one. Okay, like I said, I'll get the autograder up and running tomorrow. I'll get a video made for Project 4 tomorrow, and a few more things that some of them are that I've already talked about in this lecture video, and some others more specific details. So I'll stick around for a few minutes if anyone has any last minute questions. Otherwise, we're done with the material, and we'll see you back here next week, or we'll see you in office hours. Okay, I don't see any questions, so yep, thank you, and take care, everyone.